This podcast is brought to you by LMU Munich.
So let's formally start by saying lecture 3. So let's keep going, and I think it's better if we give a formal definition of K. Okay. So after all, I mean, you've had a whole day to become familiar with the Grassmann variables and the eta tildes, if you weren't before. So yesterday was a little bit premature to define it, but now we can actually do it. So let's define K. So if you have any amplitude that depends on the Grassmann parameters eta tildes, we define K as follows. So scale all the eta tildes by a parameter, and your amplitude will pick up a factor of this form. And whatever factor appears here would be your K. Okay? So let's see that this actually works, that this definition works. So in the one of the first examples we had was the MHB bar amplitude. Well, this amplitude has a single delta function with eta tildes. That's the only dependence of eta tildes that appears in this amplitude. So if we perform the rescaling, we clearly get that A goes to t to the fourth A. And therefore, we get that K is equal to 1, as I told you yesterday. Now let's do the general MHB amplitude. Which I'm sure you all worked out for any n, because you now knew how to build these inverse subfactors, to tag inverse subfactors, and build the super amplitude for any n. But just for the purpose of illustrating what K is, let me write what the amplitude is. So it's delta 8, where this 8 comes from the fact that we have an spinor index and a Grassmann index. And together, they make up an 8-dimensional object, so we have an 8-dimensional delta function. And here, we just have our usual part-Taylor factor and momentum conservation. Well, once again, using my definition, it's clear that A goes to t to the 8th A, and therefore K is equal to 2. Now, given this definition, it's easy to count or to determine the K of a given on-shell diagram. So for any on-shell diagram, so let me represent an on-shell diagram as follows. So there are some external legs that connect to some vertices. They themselves connect to other things. There will be internal vertices and internal edges. Okay? So can anyone come out with a rule for finding out how this big animal scales under T, under that rescaling, just by looking at the properties of the graph? In other words, I want to find a formula for the K of this graph in terms of the number of y vertices be the number of black vertices and any other property that I might need in the graph. So I'll give you a hint. Another property that we need is the number of internal edges. Well, it's clear that every white vertex, right, if I rescale everybody on the outside, which is the only thing that I should do, I should also rescale the ones inside, right? But if I do that, then the white vertices will pick up 1 power of t to the 4th. So each white vertex will contribute 1 unit to k. The black vertices will pick up 2 powers of t to the 4th, so they will contribute 2 units to the k. But each internal edge comes with an integration over eta of that internal edge. And a Grassmann measure contributes what? If I rescale the eta, what do I get? Well, since this is a Grassmann, this is a fermionic, this is a Grassmann integral, the measure scales in the opposite way to the bosonic ones, right? So I pick up at 1 over t to the 4th. So I pick up minus 1 unit of t to the 4th. So the k of this object is minus 1. So for every internal edge, I pick up minus 1 unit of k. So that's the definition of k. Let's check that it works. Of course it's correct, but it doesn't hurt to check in things that you already know. So this is the computation we did yesterday. So let's check. The number of white vertices is 2. The number of black vertices is 2. And the number of internal edges is 4. So you get 2 plus 4 minus 4 is 2. So that works out fine. Okay? And now you see why in the exercise I gave you yesterday, if you have any object with k equals 2, any diagram with k equals 2, I told you that you can attach to it what I call an inverse subfactor. And you still get something that had k equals 2. So how can you see that? Well, this was k equals 2. Now you're attaching 2 internal indices, these edges which were external now become internal. So you have the k that you had before, so the new k is the old k. You're adding 2 white vertices, 1 black vertex, and you're also adding 4 internal edges, so you have to remove 4, and that means that this operation preserves the k of the diagram. Okay? So that's why if you started with an MHP amplitude, you will end up with an MHP amplitude. And as I said yesterday, this k corresponds to the number of negative helicity particles in the all-gluon amplitude corresponding to this particular diagram. Now, let me introduce a new operation. Well, perhaps can be called all, but it's a new way of thinking about the operation. So here is the operation. Given any on-shell diagram with any k, so you have any k, okay? So let me represent whatever value of that object takes as Okay? It's some function of dual super twistors, W1 through Wn. So you have okay, so this is anything that you can imagine. It doesn't have to be an amplitude. It doesn't even have to be planar. It could be just any crazy graph that you can come out with. So that's this object. Then the new operation is the following. Attach what is called, well, I won't tell you how it's called. Let's figure out let's figure out the name after we do it. Attach the following. So you have your diagram. So to legs 1 and n, you're going to do the following. Okay? Just tag in there a white vertex, a black vertex, and just connect them. So let's try to find out what this is. Well, let's follow the rules we had yesterday. Well, we just have to label these things, say A, B, and C. These are the internal guys. Let's also choose the way we're going to gauge fix these things. Okay? So let's choose gauge fixing for these guys. And the way we're going to choose it will again be represented by arrows. So in this case, for this guy, we have to gauge fix one of the 3 variables that appears. So I'll choose to gauge fix this one and represent it as an arrow that is incoming. These ones will not be gauge fixed, so they are arrows that are outgoing. In this case, we have to gauge fix 2 of them, right? So I'll represent that by arrows that are incoming into the vertex, and this one will not be gauge fixed, so now it's outgoing. Okay? Once again, it so happens to be a perfect orientation of the little diagram. Very good. So just to remind you, what does it mean gauge fixing in this form? It means that the matrix that I'm going to use has the following form. If this is the column corresponding to 1, this is the one corresponding to A, and this is the one corresponding to B, I'm going to have a 1 here, a TA, and a TB. And the gauge fixing in this case will correspond to a 2 by 3 matrix. If this corresponds to B and C, and this one to N, so these are the corresponding labels of the columns, then I'm gauge fixing B and C to be the identity matrix, and these 2 guys to be anything I like. So let's call them X and Y. So now we're done. We just have to use what these things are. Of course, the answer of attaching that object to my previous object will be obtained by performing an integral over the internal edges that I added, projective integrals, of my object. Now it's not W1, right? It's WA. It's not WN, but WC that appears here. Right? That's this thing. But I also have to put in these guys. So what are they? Well, the first one gives me an integral dTA over TA, dTB over TB, delta 4/4 of W1 plus TA WA plus TB WB. The second one, this one gives us an integral dx over x, dy over y, and 2 delta functions. delta 4 slash 4 determined by these equations. The equations of dotting this with the w is equal to 0 give us what the equations are. So you get wb plus x wn, and then delta 4 slash 4 wc plus y wn. But now you see how trivial this computation is, right? We already have two nice projective delta functions, one here and one here, with their corresponding measures to become projective delta functions. So that's really nice that it shows up just like that. In other words, this thing is nothing but delta 3 slash 4 wb comma wn delta 3 slash 4 wc comma wn, right? So I can perform the wb and wc integrations and get a single integral over wa 3 slash 4 f of wa w2 wn minus 1. wc has now been fixed to be wn. So that's quite surprising. We did nothing to wn. The function depends. It has the same dependence as the original one on the twistor n. Very good. And we have this left over. Very good.
Excuse me.
Yes.
The formula for K you wrote down, does it depend on the way you gauge fix the black and white vertices?
No.
So I wonder why then it's not symmetric with respect to W and V. So I presume the only way where we made a distinction between W and V was in the gauge fixing.
Well, no, the white guys correspond to a single delta function. So they pick up 4 powers. Remember, this is a scaling. This K is counting the scaling only on the fermionic part, right? The gauge fixing only affected the T, but I'm not counting that, right? I'm just counting these numbers. So I got 1 power from here, or 4 powers of T, which means 1 unit of K. And in this case, I have 2. I didn't use anything. I can use any gauge fixing, and I'll still have 4 here and 4 here. That doesn't depend on the gauge fixing, right? Very good. Okay, so we're almost done because we look at this. I say, well, I want to perform this integration. I have WA with a TA, and this thing wants to be together with this. That wants to be a delta 3 slash 4 of WA, comma, W1 plus TB, WN. Sorry for the mess here, but. So the final formula is that our object is equal to, we can use the delta function to carry out this integration. So we have integral. Let me also do something else. Let me relabel this, because there are not A's, B's anywhere. We have integrated them out completely, so it's silly to call this TB. Let me introduce another name. The leftover variable, let me call it Z. So this integral becomes dz over z of f hat. Now WA with this delta function becomes this combination, W1 plus Z Wn, W2 up to Wn. So that's what I got. So attaching that object, that combination of black and white vertices to anything, all it does is to introduce a shift of W1 by Wn proportional to some number, to some integration variable, and introduces an integration over it. Well, once again, this is in dual twistor space. Just by looking at it, I don't know what it is. So let's go back to momentum space to find out what this is. So how do we go back to momentum space? Well, we know these W's, all these W's are things of the form mu tilde, lambda tilde, eta tilde. So we just have to inverse Fourier transform with respect to the mu tildes to go back to momentum space. So whatever thing this thing is in momentum space will be an integral dz over z. And now we have to perform the inverse Fourier transforms. So the only ones that are really worth writing explicitly are the Fourier transform with respect to mu1 tilde, once again, I couldn't figure out why this looks so awkward. But I think, I mean, there is a compromise. Either you make this look strange, or you don't have tildes all uniformly here, right? I think I prefer to have tildes everywhere here. Looks nicer. So this one is important. Clearly, this one will also be important. The other ones just go along for the ride. I mean, they are there, but I will not bother to write them. And then we have to put in our object. So let me write this vector more explicitly. So I'm going to write it actually completely explicitly. So this is mu1 plus z mu n lambda 1 tilde plus z lambda n tilde eta 1 tilde plus z eta n tilde. Of course, I'm not going to write W2 explicitly. Or, well, let's write Wn. Okay. Very good. What should we do now? Well, first thing to check the time. Well, we want to bring this to something that looks reasonable in momentum space, something that we can recognize. So the first thing we have to do is to get rid of this thing here, because we know how to Fourier transform something that depends on mu, on a single mu here. Okay? So let me change variables. So I'm going to change mu1. I'll shift it into mu1 minus z mu n. If I perform this shift, I get back a single mu1 tilde, which is nice. Then my function is a regular function. It's the original one. Okay? So under this shift, what happens is, well, this guy picks up a shift. So you get e from here, e to the minus mu1 lambda 1, but I get a plus I z mu n lambda 1, right? Well, now it looks natural to combine this mu n with this mu n, and then I'm almost done. So this thing is dz over z, integral d2 mu1 tilde e to the minus I mu1 tilde lambda 1 integral d2 mu n e to the minus I mu n. But now I have to be careful. I have lambda n there is a minus sign here. This is plus. If I want to put it in, I have to compensate for the minus sign. Okay. The other Fourier transforms are exactly the same as the usual ones, so no problem. And I get f of mu1 tilde, lambda 1 plus z, lambda n tilde, eta 1 tilde, and the rest. Nothing here has changed, so it's all the same up to Wn. But now we can recognize this thing. This is the Fourier transform of the original function, except that it's now evaluated on a funny lambda for the nth particle, but this is another lambda. We don't care. I mean, this is just a name for that conjugate variable to the mu tilde, to the mu. So what do we get from here? Well, this thing is equal to the integral dz over z. I'm going to remove the hat because now I'm going back to the original, to momentum space. So it's not the Fourier transform of space anymore. It's not twistor space. It's the original space. F. Sorry. Said I was going to remove it. So f of what? Well, this guy is now replaced by this guy, right? So it's an f that now depends on lambda 1 tilde plus z, lambda n tilde, eta 1 tilde plus z, eta tilde n. These ones are the usual ones. And I have to be careful in the last one, because now the lambda value is this one. So the last guy happens to be lambda m minus z lambda 1. Lambda n tilde, I didn't do anything to that component here. That one came along for the right, and eta tilde n. Does anybody recognize what this is? Yes, exactly. This is nothing but a BCFW deformation of f on 1 and n. In fact, it's a supersymmetric version, right? Because we are also deforming the super variable corresponding to 1. So now we can give a name to this operation. So the new operation is called attaching a BCFW, we call it a bridge. Okay? Yeah, I haven't told you which contour I pick. Very good. I'm going to tell you in a second what to do with the contour. But at this point, I haven't done anything. So, in fact, that's a very, very good question, because if I'm not willing to tell you what the contour is, if I refuse to do that, then this operation, what it does for us, is to define a differential form, right? So the differential form doesn't have information about the contour. So it would be even better to say that the BCFW bridge, what it does for you is to create a differential form. Now you can choose to do whatever you want with that differential form. And we will certainly do different things. Okay. So now we are ready to use that. we can use that to give an on-shell diagram description of 3 amplitudes. Well, the reason is that we just discovered how to represent, in terms of on-shell diagrams, a BCFW deformation. And all we have to do is to see what to do with the contour, but we can do exactly what was done with BCFW. So let's assume, or let's show that any amplitude can be represented in terms of on-shell diagrams. So we will use induction, or we will start with we will just use the recursion relation more explicitly. So we will start with a given n and k amplitude and we are going to write this as follows. We're going to write this as an integral dz over z around z equals to 0 of the object that you get by attaching a BCFW bridge to this. Okay. Well, as usual, using BCFW, we can use a contour deformation and pick up poles of this object. But yesterday, we saw what a factorization channel looks like in on-shell diagrams. A factorization channel is nothing but literally taking these two things apart and joining them with an on-shell leg, with an on-shell edge, okay? So what do we get? Well, we get the sum over all possible factorizations of this object into smaller objects. Where the sum over I goes from 2 to n minus 2. Okay. Well, again, by induction, we can represent these as smaller objects using the recursion relation again and keep going until we end up with 3 particle amplitudes. And therefore, each term in the BCFW expansion will correspond to a given on-shell diagram. So let's use this to compute something explicitly. So yesterday, somebody was complaining that we were doing things that were too easy, that we hadn't seen anything with k equals 3. So let's fix that problem. Let's do k equals 3 and n equals 6. So this means k equals 3 and n equals 6. So how can we do this? Well, we just start and write our object. And we have to write it in all, to produce all possible terms. So we have 1, 2, 3, 4, 5, and 6. Now we have to decide what to do with the color of this guy, right? Well, one way to decide is as follows. If this guy is white, just like this one is, clearly, right? So these two guys are of the same color. That would mean in twistor space, it would mean that these two guys represent the same twistor. So that would be a singular configuration. That cannot happen, or at least it would give us, is something that vanishes for general momenta. And we are interested in things that don't vanish for general momenta. So this guy cannot possibly be a white vertex like this one. It has to be a black vertex like this one. Okay. So there is a single possibility for the color of this guy. Now, if this is a black vertex, what should be the k of this amplitude so that the k of the total graph is equal to 3? Can anybody quickly compute it? So we need the total k to be 3 always. Okay? So we have to determine the k of this one. This one could be a k equals 2 or a k equals 3 amplitude. So you can just say a number, you have 50% chances of getting it right. Well, let's see. Let's call it K prime. So what is the K of this diagram? Well, you have 1 from here, 2 from here, 2 from here, minus 4 from these guys, and K prime from this guy. And this better be equal to 3. And that means that K prime is 2. Okay? So our little 5-particle object here has to be an amplitude with K equals 2. Well, yesterday, as an exercise, you were supposed to compute the on-shell diagram, or show what the on-shell diagram was for a 5-particle amplitude. So one possibility you probably found was it could have been something like this. Right? I'm sure everybody did it, right? This was the on-shell diagram for an MHP amplitude, a 5-particle MHP amplitude. And what we are told here is to attach this to this diagram. This thing is this, so we want to attach it, and all we have to do is to put here 6, 1, and 2. So this is the on-shell diagram corresponding to this term in BCFW, in the BCFW expansion of this. What's the next term? Well, again, we repeat the game. 1, 6, 2, 3, 4, 5. Now we don't have much choices, right? Because we know that the only 4-particle amplitude that doesn't vanish has K equals 2. So either these guys with K equals 2 give me something that is K equals 3, or it doesn't contribute. So let's check. So this is K equals 2, so that would be 2, 4, 6, 7, minus 4 is 3. So that works. Okay. So these are K equals 2 4-particle amplitudes. But 4-particle amplitudes, those are trivial now, right? So what are they? Things like this. Right? So these are the 4-particle amplitudes. They are joined here, and they come together with a 1 here and with a 6 here. So that's the next on-shell diagram. And the last guy, because there is only one more possibility, is the case where we have 5 here all by itself, 4, 3, and 2. And now we have to find out what the K of this guy is. Very quickly, we have 1, 2, 3, 4. 4 minus 4 is 0, so this guy better be 3 to give me K equals 3 as a total object. But this is a 5-particle K equals 3 guy. You'd say, well, but we haven't done it. Well, no problem. Just take the MHP1 and apply a parity transformation. If you apply a parity transformation to an MHP 5-particle amplitude, you end up with an MHP bar 5-particle amplitude. What do you think parity is in terms of on-shell diagrams? If you want to apply a parity transformation to a given diagram, what do you have to do to the diagram? Yes, but in terms of the graph, is that something we can easily do on the graph? If you flip the helicities, that's a good starting point. What would happen to the black and white vertices? Exactly. They just interchange. So you just, well, most of you are too young to know that, but you do the carbon copy. I've seen that. So you take this guy, and then you reverse all the colors in the graph, and you get the parity conjugate version of it. So that's what we want to do here. Well, that thing is something that looks like this. Attached to 5, which is attached to 6, and 6 goes to 1. Okay? Sorry?
K would go to n minus k, but in this case it's the same. Yeah.
For 5 particles.
For parity.
Oh, yes, yes, yes. So in this case, it's the same, right? So that's a very good observation. Now, you have this, the sum of these 3 on-shell diagrams. If you apply parity, you get now a representation where you flip all the colors, right? But this thing is supersymmetric. So, well, as long as you take care of the etas and the eta tildes, then you should get something that is consistent. Okay, so we have this. This is our first non-trivial 3-level amplitude. Yesterday, somebody also complained, saying that, well, are we only going to do 3-level? In these lectures, we have been going up to 5 loops, right? Well, let's actually do a 1-loop computation. We have to start somewhere, right? Well, let's not even call it a 1-loop. Let's keep our study, before we do the 1-loop computation, let's keep our study of on-shell diagrams, just for their own sake. So, more general on-shell diagrams. So, now that we have this BCFW bridge operation, we can construct more general on-shell diagrams, starting with a very simple one. So, let's start with this guy. So I have to warn you that I'll start, I'll keep building up on this guy, but I'm not going to draw it again. So I'm going to erase and attach more things to it. So what do I want to do? Well, we know what this is. This is, the original object is the 3-level amplitude, MHB amplitude. Okay, that was in step 1. Next, what I want to do is to attach a BCFW bridge to these 2 guys. Okay. Why do I want to do this? Well, the standard reason, because I can. So at this point, no reason whatsoever. So what do I get in step 2? Well, step 1 was to draw the original picture. Step 2 is to attach this first W bridge. So according to my rule, all that happens to this guy is that I have to integrate over some variable. Let me call it the XX. Okay? And according to this rule, if I look here, I shift these guys and these guys. So I'm shifting lambda 4 by lambda 1. The shift was designed to leave this invariant, right? If you have never seen that, do the computation. So, of course, the BCFW shift was originally designed to leave momentum conservation invariant, but the supersymmetric part was only found later on, and is actually designed so that the supersymmetric version of the momentum conservation is also invariant. So nothing happens to this guy. Okay? So from now on, I will not write that, and I will only keep track of the denominator. So this thing will be invariant under everything that I'm going to do. So it will just stay there, okay? So according to that, I'm supposed to shift lambda 4 in this step. So let me do it here. I'm supposed to shift lambda 4 by lambda 4 minus x lambda 1. So you get integral the x over x, 1 over 1, 2, 2, 3. Now I shift lambda 4, I get 3, 4 minus x, 3, 1, and 4, 1. This one is unaffected. Okay? Well, next step. Let's apply a BCFW bridge to these two guys. Okay? Which one I'm going to do is the following. I'm going to take black here again and white here. Okay? Well, that's trivial again. All I have to do is something on this object, because I gave you the definition on any object. So I can do it on the object that I got before. And what I do is to shift lambda 2 by... Oh, sorry. Oh, somebody should have said, right, that this is 2. Right? So this was wrong. It's just that there I shifted n, and n here is 4, but of course it's not. That's not what I'm doing. So this is 2, 3 minus x, 1, 3, 3, 4, 4, 1. Now I'm shifting lambda 2 again, but shifted by 3. So let me shift it by a variable y, lambda 3. And now my new object has two integrations, dx over x, dy over y, and another integration variable. And that thing will now shift this one. So you get 1, 2 minus y, 1, 3 times what I had before. Okay? Now you can complete the dots, right? So what's the next step in the pattern? Well, the next step is to attach another BCFW bridge here and here. Why did I shift this one and not this one? No, sorry, what was the question? I shifted everything, but sometimes the shift doesn't do anything because this is a 1, right? And this is a 3. So if it's gone, it's gone, but I'm supposed to shift everything. Okay, so now I do this one. So this is step 4. And step 4 tells me that I'm shifting lambda 4 by lambda 3. Let me call it z. So you get so let me not write the whole thing again. So just this guy goes here. So I'm shifting 4 by 3. This one is unaffected. And this one picks up a 4, 1 minus z 3, 1. And of course, this diagram looks weird unless I do the last step. The last step would be attach a BCFW bridge here to this guy. Okay, this one I'm going to write because it's the final answer. So this one is shifting lambda 4 by lambda 1. And the answer is then dx, dy, dz, dw, x, y, z, w of a bunch of things. Let me now do something to what I'm going to, well, yeah, I shouldn't be that lazy. So the new shift affects this guy. So you get 3, 4 minus W, 3, 1. Okay. Very good. Well, as usual, the formulas tell you what they want you to do with them. And this one, note the factors that appear here, 1, 2, 2, 3, 3, 4, 4, 1. It's as if it wants you to factor that out. So if you did, so the answer, or that diagram, will be what we had, the supersymmetric delta functions, the momentum conservation. We're going to factor this, this, and this from the formula. Times, now we're going to get integrals dx, dy, dc, dw, have x, y, z, and w. Now, every time I factor something out, I ended up with something that looks like an integral, say, dx over x, 1 over 1 minus x with something. Right? So I factor 2, 3 out, and there is something in here. But note there is something interesting. This measure is invariant under rescalings. So I can rescale this to 1, and I don't pay any price. Okay? In particular, let me rescale it to -1. I don't pay any price either. So what I get is a bunch of factors of the form 1 plus x, 1 plus y, 1 plus z, 1 plus w. But also note the following. If you have an integral dx over x, 1 plus x, this is nothing but, up to a sign, d log of x over 1 plus x. So what we are learning is that this on-shell diagram is nothing but an integral or a differential form over 4 d log functions. So let me put them here. So we have d log of x over 1 plus x, d log of y over 1 plus y, okay? So what could this be? Well, it has 4 integration variables. So any loop integration in 4 dimensions, at least a one loop integration, has 4 integration variables. Too bad that this looks too simple to be any sensible integration that appears in a Feynman diagram calculation. Or is it? Could it be that actual Feynman diagrams, actual integrations, become something so simple as just d logs of trivial functions? And if that's the case, then it's amusing that this on-shell diagram would then become, it would have physical meaning. So let's keep this formula here. And let's go back to the 90s, or even earlier. I'm not sure about the history, but let's write down the explicit, just look it in the literature. Explicit, 1 loop, 4-point amplitude. partial color ordered amplitude. Just open any review paper, and you will see it there. This guy happens to be the MHP amplitude, the 3-level one, divided by times an integral of the form d4L over L squared, L minus P1 squared, L minus P1 minus P2 squared, and L plus P4 squared. Multiply it in the numerator by 1, 2, 1, 2, 2, 3, 2, 3. That's the answer. Well, this loop integration corresponds to the integration that you will get in a scalar field theory with momenta P1, P2, P3, P4, and loop momentum defined to be this, and all legs outgoing. Okay? So if you haven't seen it before, it doesn't matter. This is the answer. I mean, that's the full one-loop 4-point amplitude. Of course, you probably have seen that many times. This amplitude is infrared divergent. It needs a regulator. Well, but that happens on the physical contour. If I want to think about this as a differential form, I don't have to worry about that, because I can choose any other contour where this is finite. It might not have a direct physical meaning, but I'm only concerned at this point with the structure of the differential form. So what the contour is not going to be relevant for the discussion I have now. Very good. So what do I want to do? Well, I want to use a little trick. I want to rewrite this as the diagram is telling me to. I don't want to solve for momentum conservation. I want to think about each of these guys as being off-shell particles, but each one of them independent from each other. And I want to impose constraints as they go. So let me just check the convention, because if I don't get the conventions right, so what's the convention? L. So I want to call this L1 and this L2, this L3 and this L4. Yeah, that's what I want. Okay, so I want to think about this as off-shell particles, each one of them independent from each other, and I want to write down what the diagram is telling me with the corresponding constraints. So what would that be? Well, I have to take this guy. Yeah, in fact, so maybe just use this. Let's rewrite this. So let's just study that. So I'm going to write it as follows. I'm going to write it as an integral product from I equals to 1 to 4, d4 li squared, right? Because that's what happens. These propagators are nothing but the corresponding propagators here, times a bunch of constraints. And what are the constraints? Well, the constraints are that momentum conservation has to be satisfied at each vertex. So if I have L1 coming into this vertex, okay, it better be equal to P1 and L2. The same thing at the next vertex. where I have L2, L3 minus P2, delta 4, L3 minus L4 minus P3, and delta 4, L4 minus L1 minus P1. Okay? So I haven't done anything really deep. In fact, so I just made the equation, the integral look more complicated. But here comes the simplification. It's been known for a long time, since the beginning of relativity, that any vector can be written as the sum of two null vectors. So why don't we decompose these loop integration variables in that form? In other words, let me take each of the LIs and write it as follows. Okay, so Li has 4 degrees of freedom. I want Li, little Li, to be null. So that implies that only has 3 degrees of freedom. And therefore, and tau is 1. And that implies that my Q, which is also null, has to be fixed. Okay? So that's my change of variables. So an exercise, which is actually trivial, is the following. Show that this measure under this change of variables becomes d tau over tau times d for Li delta Li squared. So of course, this is what imposes a constraint that this guy is null. But I'm calling it little l to remind myself that the constraint is telling me there is a null vector. Note that there is no dependence of Q here. It's all in the contour. Okay? It's really in the contour. If you want to integrate, you have to tell me what contour you would like for this guy, and that will tell me what the contour is for this guy, which depends on what reference spinor or what reference vector you choose. So if we do this, and we apply that to our integral, so our integral, let me call it I, becomes integral 1 to 4 d tau I over tau I Well, it also has the other part of the measure, product from 1 to 4, d for Li squared. And now we have these guys here. We have L1 minus L2 minus P1, and now P1 will be modified by all these extra pieces that come from these guys. So let me redefine this to be something that depends on tau. So what is this P1 of tau? It's my old P1, but now there is a shift coming from L1, and there is one coming from L2, right? Now this is P1 of tau. It's just a trivial definition. I haven't done anything yet. The next one is L3 minus L4 minus P3 of tau. Sorry. Shouldn't have been that. Should have been 2, 3, 2. Where now P2 is equal to P2 minus tau 2 Q2 plus tau 3 Q3 delta 4 L3 minus L4 minus P3 of tau and delta 4 L4 minus L1 minus P1 of tau. P4. Tau. So I have my other ones. Okay. Now, isn't this very interesting? Look at just this piece. This is exactly like a one-loop diagram where you have, instead of P1, you have P1 of tau, P2 of tau, P3 of tau, 4, and here you have L1, L2. But these guys, their propagators have been cut. So by now you're experts in cuts. You have been cutting things all over the place this week, right? So these guys are nothing but the cut of this propagator. You are cutting this guy. So that's what it means to cut. So it's as if you had this guy and you were cutting this thing. And I hope you have been told what this thing is. This cut of this integral is something very easy to compute. And it's nothing but 1 over the S channel, the kinematic invariant S of the diagram, which now depends on tau, times the kinematic invariant T of the diagram, of the integral, which now depends on tau. That's the answer of this integral. So we just did this integration. Well, if you don't believe me, well, you can do it yourself. Know that these delta functions completely localize 3 of the guys, leaving you only 1 loop momentum integration variable, but you have 4 constraints on that single loop momentum variable. That completely fixes the value of that thing. It turns out that there are 2 solutions to that, and if you evaluate this, you compute the Jacobian of the change of variables, that would be the Jacobian in either of the 2 solutions. Okay? So that's an exercise if you haven't done it. But if you did this week 5 loops and cutting everything, you probably cut this one, I hope. So you have this guy. So what I'm saying is that I just did this integration for you. So there is no more integration over the LIs. This is the answer. So I have traded all the complicated integrations over all these variables for just 4 integrations over variables tau. Well, that's starting to look good, right? Look at the board on top, or here. Could this thing be related to this computation we did before, or to that particular diagram? Well, the answer is yes, but we have to make a choice. And once again, the choice is a matter of convention, but let me actually use convention. For the reference vectors, let me choose the following. They are reference vectors. I can choose them to be whatever I want. So there is no wrong choice, but there is a convenient choice, again. And this is a convenient one. So why is it convenient? Well, look at what P1 is. Yeah, well, let me do this here. let's look at what P1 is. P1 of tau. Is that a null vector? P1 of tau. Well, let's see. What is Q1? Lambda 4, lambda 1 tilde, Q2, lambda 2, lambda 1 tilde. Now there is a lambda 1 tilde as a common factor. So what I have here is lambda 1 minus tau 1, lambda 4, plus lambda 2, tau 2, lambda 2, times lambda 1 tilde. It is a null vector. So that's great. This P2 of tau now becomes lambda 2 tilde minus tau 2. Q2 has a lambda 1 tilde plus tau 3. Q3 has a lambda 3 tilde. P3 of tau is equal to lambda 3. Well, I didn't write it there, but I have it here. Plus T4 lambda 4 minus tau 3 lambda 2 lambda 3 tilde. And P4 of tau is lambda 4 okay. So what have we done? Well, we just made a convenient choice for the reference guys. We computed this, and now we want to compute what this is. Okay. Remember, we also have these factors. Okay. So these factors will be important later on. So let's do this computation quickly. So we said that the whole integral is nothing but 1 over s of tau times t of tau. Well, this thing is equal to 1, 2, 1, 2, 2, 3, 2, 3, but with the new vectors, with these guys. So I have to be careful and remember that 1 depends on tau, lambda 1, lambda 2 tilde depends on tau, lambda 3 depends on tau, and lambda 2 tilde depends on tau. So let's compute what they are. So this thing is equal to 1 over. So lambda 2, this thing, 1, 2 gives me 1, 2. This drops out. I only get contribution from here. 1, 4. This one gives me 1, 2. Only contribution from here. Next one, this one gives me 2, 3. This drops out, we get tau 4, 2, 4. This one, the last one, is 2, 3. This one drops out, and I get this contribution. Well, isn't this nice? This is starting to look like this. But you would say, well, it's clearly wrong. Well, this one is clearly right, because it comes from the answer. But this one looks very, very different from this. Well, but let me do the same thing. Once again, I want to factor this out. 1, 2, this 1, 2, 2, 3, 2, 3. Okay? So if I did that, just like I did it here, what do I get? And if on top of that, I remember that I have this factor in the numerator, I have this 1, 2, 1, 2, 2, 3, 2, 3. Now I factor out these guys. I'm going to factor this, 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 and this. I get exactly this, right? I get 1, 2, 1 minus tau 1 times song A, 1, 2 times 1 minus tau 3 or plus tau 3 times some b, 1, 2, 3 times 1 plus tau 4 times some c, and 2, 3 times 1 plus minus tau 2 times some d that I don't care at the moment what they are. This cancels this, this one, this one, this. And we're almost done, because once again, this measure is invariant under rescalings, so it can absorb all these guys and end up with something that looks like integral product over I from 1 to 4 d log of tau I 1 plus tau I. So surprise, exactly the integral that has been known forever can be written as a product of 4 d logs. That, quite surprisingly, as far as I know, has been unnoticed for a long time. And the factor we got in front, I mean, of course, when we did the integral and we got the answer, we also got a momentum conservation delta function, right? These 4 delta functions, 3 of them localize 3 of the L's, leaving 1 of the L's as an integration variable, and the 4th delta function becomes momentum conservation. That's where it came from in the first place. So there was a momentum conservation here left over. So we get this thing here. And recall what we got in front was the MHB amplitude. So we ended up writing the one loop MHB amplitude. So this is equal to exactly, well, I don't have to write it, to exactly this. Just relabeling the variables, we get exactly what we got before. So surprise, this on-shell diagram not only has physical meaning, it has all the physical meaning you need. It's the full one-loop 4-particle amplitude, all contained in a single, purely on-shell structure. Okay?
If I want to compute this log x1 x in product,
Yes.
you said I should be making this a differential form, or?
Yeah, well, this is a differential form. And now if you want to integrate, you have to specify the contour. So if you choose a real contour, you will get logarithms. Of course, it will be divergent. You have to introduce a regulator, and then you will get what you get. But as far as thinking about the one-loop amplitude as a differential form, that's the answer. So thinking about the differential form is what is now known as talking about the integrand of the object. Okay.
So the contour depends on the momentum.
The contour, the physical contour is the contour where the momentum L, this L belongs to R4. So you can think about L originally as a general variable in C4, and you're choosing a middle dimensional cycle or a middle dimensional object in C4 to be your contour. This is one choice.
So what I'm saying is that integral, that would depend on P1, P2, and P4, right?
This integral?
Yeah.
Yes, so these are the momenta of the external particles, yes.
So what I'm saying is that integral will also have to depend.
Yes, but now only through the contour.
So the contour depends.
Oh, yeah, sorry, I didn't. Yes, that's right. Well, you see, but only through, that's a very interesting question, only through the choice of the reference guys. That's the only place the information of the external data enters. But you see that that choice was crucial. It was so crucial that I didn't want to mess it up, and I had to look it up, right? So that choice had to be done exactly as I said. So, and it depends strongly on the external data. So that's the only place. Imposing that Li is equal to that thing over on the top of the blackboard, and imposing this condition locks the value of tau I to be something that depends on the external data. Okay, so before we go to the break, let me just propose an exercise that you can do during the break. And it's the following. So let me see. Yeah, this might actually be. Take this guy, okay, this diagram here. Use merge and expand operations and square moves. To convert this, okay, show that this is exactly equal to the following. Yeah, so I think I got the, well, doesn't matter. Doesn't matter. Yeah, I don't want this ordering. So allow me to, of course, the ordering, I mean, I can reverse this. It doesn't really matter. So I can put 2 here, to keep 3 and put 4 here. That doesn't matter. So now I can put, so this would be 1, 2, 3, and 4. Okay. Very good. So that's what I want you to try. Show that this, by merge and expand, by uses of both operations, maybe many, many times, who knows, you can take this diagram into this diagram.